What that allows us to do is rewrite g of x as the product of x minus 3 and 2x squared plus 11x plus 5. We only need to worry about factoring this reduced polynomial now, 2x squared plus 11x plus 5. This is a quadratic, so we could try to factor that. We get x minus 3 times 2x plus 1 times x plus 5. So here we have our function g of x in factored form. To find the remaining zeros, set our last two factors equal to 0 and solve. We get 2x plus 1 equals 0. X plus 5 is equal to 0. So solving this equation, we get 2x equals negative 1, or x is negative 1/2. With this equation, we'll end up with x is equal to negative 5. Therefore, the zeros for our function are negative 5, negative 1/2, and 3. Now, if you notice, these are three rational zeros as well, and if we look back in Part C at our list of potential rational zeros, we'll see that each of these occurred in that list. Our function in completely factored form is then x minus 3 times 2x plus 1 times x plus 5. Now that we've found the zeros for our function, we're going to turn our focus to the intercepts. In Part E, we're asked to find the x and y intercepts of the graph of G. In the previous part, we found that the zeros of the function were negative 5, negative 1/2, and 3. We've also seen that x-intercepts and zeros are essentially the same thing, so our x-intercepts are negative 5, negative 1/2, and 3. To find the y-intercept, we need to evaluate g of 0. G of 0 is 2 times 0 cubed plus 5 times 0 squared minus 28 times 0 minus 15, which is just negative 15. So our x-intercepts are negative 5, negative 1/2, 3. Now our y-intercept is negative 15. If we want to write ordered pairs, the intercepts would be negative 5, 0, negative 1/2, 0, 3, 0, and 0, comma, negative 15. Next, we're going to determine whether the graph crosses or touches the x-axis at each x-intercept. If we list our intercepts, we had negative 5, negative 1/2, and 3. And we're interested in the behavior of the graph at each of those x-intercepts. Now, whether the graph crosses or touches at an x-intercept is determined by the multiplicity. We factored g of x as x minus 3 times 2x plus 1 times x plus 5. If we look at the exponent in each of these factors, you see that the exponents are all 1, which is an odd number. Each of these factors gives us one of our x-intercepts. The negative 5 comes from the factor x plus 5. The negative 1/2 comes from the factor 2x plus 1. And the 3 comes from the factor x minus 3. Since each of these factors has an odd power, the multiplicity is odd. And the behavior for an odd multiplicity is that the graph will cross at each of these x-intercepts. Had the multiplicity been even, the graph would have just touched the x-axis at the x-intercept. But each one of these had odd multiplicity, so the graph will cross at each one. In Part G, we're looking for the power function that the graph resembles for large values of the absolute value of x. The power function is given by the term with the highest power of x. In this case, we get y is equal to 2x cubed. It's the term in our function with the highest power of x. So the graph of g will resemble the graph of 2x cubed for large values of the absolute value of x. We're just about ready to sketch the graph of our function. before we do sketch the graph, we'd like to look at the behavior of the function near each x-intercept. In determining the behavior of the graph of our function near each x-intercept, let's first note that our x-intercepts were -5, -1/2, and 3, and that we could write our function g in factored form as x minus 3 times 2x plus 1 times x plus 5. So we look at the behavior near each of the 3 x-intercepts that we have. We'll start with -5. To find the behavior near -5, we're going to evaluate the function at -5 in each of the 2 factors except x plus 5. So we're going to evaluate g of x. In this first factor, we'll let x equal 5. In the second factor, let x equal -5. But we're not going to evaluate this third factor at -5 because that would give us 0. So near -5, g of x is approximately -8 times -9 times x plus 5. So if we put in -5 for x, -5 minus 3 is -8. 2 times -5 is -10, plus 1 gives us the -9. Again, we're not using the x plus 5 factor because we're looking at what happens near -5. This is equal to 72 times x plus 5. So near -5, the graph of g will look like a line with slope 72. Next, we'll look at the intercept -1/2 and do the same thing. We're going to let x equal -1/2 in each of the factors except for the factor that gave us this intercept. That is 2x plus 1 in this case. So g of x is going to be approximately -7/2 times 2x plus 1 times 9/2. If we simplify this, we'll get -63/2 times x minus 63/4. And so near -1/2, the graph of g will look like a line with slope -63/2. And our last intercept was 3. So we look at the behavior near 3. Following the same procedure, we're going to let x equal 3 in the 2 factors that did not give us this x-intercept. So g of x will be roughly x minus 3 times 7 times 8, which is equal to 56 times x minus 3. So near 3, the graph of g will look like a line with slope 56. The last part asks us to put all the information we've just obtained together so that we can get a graph of g. If we put all that information together, we get this graph for our function g. To actually obtain the graph by hand, we would need to evaluate the function at several different values for x to help determine the scale that we should use and also to help us smooth out the shape of the graph. If we look at the graph, we notice our x-intercepts. We had -5, we had +3, and we had -1/2. Those are our x-intercepts. And we had a y-intercept of -5. Notice also that we said at each of the x-intercepts that the graph would cross the x-axis there. And we see that that's exactly what's happening. At -5, -1/2, and 3, the graph crosses the x-axis. For our power function, we said that g of x would look like the graph of y equals 2x cubed for large values of the absolute value of x. We know that this is a cubic polynomial. The left end goes down, the right side goes up. And so this is in keeping with our power function 2x cubed. Some additional points would help smooth this out. We see our scale is from -6 to 6 along the x-axis and from -60 to 60 along the y-axis to give us a pretty good picture of what our function looks like.